This video clip, we're going to take a look at the concept in chemistry known as entropy. When we speak of entropy, entropy is a means of measuring a system's disorder, how much organization or disorganization is occurring as a reaction proceeds. If the entropy in a system is increasing, that's an indication that the disorder in this system is also increasing. Now, on the other hand, if the entropy of something is decreasing, that would be an indication that the disorder is decreasing, which is another way of saying that the system is getting more orderly or organized with a decrease in entropy. An example would be merely the physical state. As we go from a solid to a liquid to a gas, the entropy in our system would be increasing as we go to a higher and higher state of disorder. This would be true for any material as we go from solid to liquid to gas. What's occurring is the disorganization of the material is increasing, and with an increase in disorder, that would be indicative of the entropy increasing, going solid to liquid to gas. Another example of a change in entropy would be merely having the same phase. In this case, we have liquid water at 25 degrees Celsius, and it changes to liquid water at 50 degrees Celsius. Now, if we consider with particles, as their temperature goes up, what happens is the particles have more motion, more movement. The increase of movement of these particles in the same phase, liquid phase, is indicative of a greater state of disorder at the higher temperature, so our entropy has increased as the water went from 25 degrees Celsius to 50 degrees Celsius within the same phase. Another indication of a change in entropy is the change in the number of pieces. In this case, the phase on both sides is gaseous, so the entropy change wouldn't come from a phase change, but rather if we notice on the left side we have one piece, a single Cl2. On the product side it's changed to two pieces, two separate Cl atoms. With this change in the number of pieces, where we've gone from one piece to two pieces, because the number of pieces has increased, that's an indication that the disorder or the entropy of the system is increasing as we go from one piece to two within the same phase. Now, in working with entropy, entropy is represented by S. It is possible to calculate a value for a change in entropy in a particular chemical reaction. For example, our earlier example, we had Cl2 turning into two separate Cl atoms. This change here would be our change in entropy of the reaction. In this case, we have the entropy increasing, and with an increase in entropy, we'd notice that our change in entropy would come out to be a positive number. Our change in entropy can be calculated by taking the final condition of our entropy, the products, and subtracting the entropy of the reactants. And in this case, because we finished at a higher level of entropy than where we started, our change in entropy would give us a positive value. Now, if we have a decrease in entropy, where we're going from a more disorderly state, in this case, say liquid water, to a more organized state, solid water, in this example, with our liquid water changing to our solid water, we'd see that our entropy is decreasing. With the decrease in entropy, our change in entropy for the reaction we would expect to be a negative number. We'd get the negative because if we're taking products minus reactants, the entropy state of our products are at a lower level than our reactants, and we're going to get a negative number for our change in entropy to indicate that the entropy of the system is decreasing. Now, taking a look at a more traditional chemical equation, it's possible in many cases to predict whether the change will be a positive change in entropy, meaning an increase in entropy, or a negative change, would be a decrease in entropy. Looking at this reaction, on the reactant side we have 2 pieces. It's turning into 3 pieces on the product side. An increase in the number of pieces would be indicative of an increase in entropy for this process. Additionally, on the reactant side, the physical state is we have a solid and a liquid, and it's turning into a solid and a gas, which would be an indication also of an increase in entropy. So in all likelihood for this reaction, we could predict that the change in entropy for the reaction is going to be a positive, and the entropy in this system is increasing or going to a greater state of disorder as we move from reactant to product. Now, it's also possible to get a mathematical value for our change in entropy by taking the entropy level of our products and subtracting from it the entropy level of our reactants. Using known values obtained from our pink sheet with the known values, we can get a value for our total amount of entropy of the reactants and our total amount of entropy for the products. Find that our value, our total for the reactants entropy, is positive 0.1595 kilojoules per Kelvin mole, and our total entropy for the products is a positive 0.4005 kilojoules per Kelvin mole. Taking this information and using change in entropy of reaction will be our products minus reactants, we can calculate that for this reaction our change in entropy is a positive 0.2410 kilojoules per Kelvin mole, indicating for this reaction as we go from reactant to product there's been an increase in the amount of entropy or disorder to the system.